Alright, so we had to take a little break. So what the lowering operator does, to remind you after all this, is when it acts on an eigenstate, the nth eigenstate, with the energy E, and we're going to convert to Brockett notation here, state n. It produces a state with energy E equals E sub n, or with E sub n minus HW. It lowers it by H bar W. Well, what about our ground state, psi sub 0? Well, the ground state is defined as the state with the lowest energy, and so you can't go lower than your lowest energy. So the corresponding state should have probability 0. There should be 0 probability of the state having having energy less than the ground state energy, which means that state must be equal to 0. So basically what that means is when you act the lowering operator on the ground state, here I'll go back to psi sub 0. I meant to put psi sub 0. It should equal 0. Well, that gives us a differential equation. And we'll plug back in, remember that the momentum operator is negative IH bar times the derivative. So the little factor doesn't matter because it cancels out with the 0. We get that this will define our ground state, psi sub 0, no wait, no, you're good. You know what you're doing. Plus H over MW this. I'm going to rearrange the terms in this equation. Negative MW over H bar X times psi equals psi sub 0, the derivative with respect to X. I'm going to rearrange that equation like that. Well, you can just pull this out there, a factor of, and you can take this delta X and put it here. And now we want to integrate. Indefinite integration. Plus a constant equals 0. Well, that's just the integral of 1 over x times dx is just the natural logarithm of absolute value of x. And that's just going to be x squared over 2 constant plus, minus MWH x squared equals, arrive at that equation there. Okay, apparently we've summoned something.
That's Siri.
Summoned Google. Now we're going to exponentiate this, and that gives us a new constant times e minus e to the power of negative x squared. This is our ground state wave function. which corresponds to the state of lowest energy. We can determine the factor of A by considering that the wave function is, by definition in quantum mechanics, a probability amplitude, which means that basically the probability of being somewhere in space, integrate over all space, complex conjugate, must equal 1, or in Brockett notation, the inner product of psi of this ket with itself is equal to 1. And in our case, so we're going to compute that there. And we're going to determine what A has to be. We're going to assume that the factor A is a real number. It's not super important, but so our integral will equal 1 equals A squared plus negative infinity equals complex conjugate of this. There's no imaginary terms, so we don't have to do anything to that. We can just absorb that into one factor there. Marker. Now, this is where you absorb terms. We're going to substitute, equals y squared. MW over h bar times x squared equals y squared. We're going to substitute. The bounds, this is a finite number. So when you multiply infinity by a finite number or divide it by a finite number, it's still infinity because it's huge. So the bounds aren't going to change of the integral. Well, we can now rewrite this as dy h over mw a squared dy. And this is a very famous integral. Basically, there's all kinds of ways to solve it. Like you can do it with a Fourier series or of e minus x squared if you want. We're going to calculate. Here, I'm going to write this over here. It's not just for a little guide. We're just going to focus on this little integral here. We're going to say I squared. No, we're going to say that this integral is equal to I. Big I, not like imaginary number I. Well, let's square it and consider that it's equal to, just a change of variables over here. So I squared equals now this is best solved in spherical coordinates. We're going to change the coordinate system that we're using. we're going to use a coordinate system where x equals r cosine of theta, y equals r sine of theta. And r ranges, instead of x and y varying between negative infinity and infinity, r will range between 0 and infinity, and theta will range from 0 to 2 pi. Now, when calculating area changes, well, let's just see how a total differential changes. D of x equals, you have to count for the change in r, dx d theta, and for d, the differential of y, when you change r and theta, it'll change by this much. Well, this is basically just a linear transformation. Dx of dr, dx of d over d theta, dy over dr, dy over d theta, dr d theta, and sorry, dr d theta. And basically, when the determinant of a matrix, this is a matrix here, the determinant of a matrix calculates how much the area squeezes, or when you perform a linear transformation. So basically you're going to calculate determinant of dx over dr. This is called the Jacobian, I believe. Dy over dr, dy over d theta, d theta equals our area element dx dy. And in our case, the derivative, hold on, no. In our case, the derivative of x with respect to r is just cosine of theta. Derivative of x with respect to theta is just negative. Can you see this all right? Okay. Negative r sine theta. Derivative of y with respect to theta with respect to r is just sine theta. And derivative of y with respect to theta is r cosine theta. And that's just the rotation matrix, well, with the factor of r. Now to take its determinant, you multiply both sides together and then subtract the other cross. So r cosine squared of theta minus the negative signs cancel, plus sine squared of theta dr d theta. And those are just equal to 1, because cosine squared plus sine squared of anything is just 1. So we're left with and x squared plus y squared, same thing with the signs, it'll just go to negative r squared. And we're going to integrate from 2 pi to 0 over d theta, r times dr d theta. There's no thetas in this equation, so you just multiply it by theta basically and subtract over the bounds. So that's just going to be 2 pi. That's easy. We can erase that. We can substitute and get r squared. R times dr is just equal to dr squared, 1/2 dr squared. And we can say r squared is now u, and infinity squared is just infinity, and 0 squared is just 0. So infinity u du, and then the factor of 1/2 just takes it to pi. And that's equal to pi negative e minus u over infinity to 0 equals pi negative e plus e0. As that goes to infinity, the e to the power of infinity is very huge, so 1 over that is tiny, and that goes to 0, and e to the power of 0 is just 1. So that means that our whole equal to pi. Our integral squared is equal to pi. That means that our original integral is the square root of that, and it could either be positive or minus pi, or positive or negative pi. We're gonna break this integral up to like this, from 0 to infinity, and then negative infinity to 0. We're going to do a substitution. We're going to change that to negative. We're going to change that to negative sign, and then that doesn't affect anything. So, but when you minus that, it switches the direction. So really, this is just before you perform the definite part of the integral, where you do that. I need to stop using my finger. This will just be a function g of x. And then you'd perform g of infinity minus g of 0. Well, the derivative g of x is just by definition e minus e to the power of minus x squared. From the entire bounds of this, from 0 to infinity, this is a positive number. So that means that the derivative over the course of bounds of g of x is always positive, which means it always increases from 0 to infinity as x increases. Which means that since infinity is greater than 0, that g of infinity minus g of 0, it's going to be greater than that. So this is actually going to be a positive number, which means that our integral must equal positive square root of pi. There we go. So now we're going to go back to that. The whole thing is just going to be negative pi. Oops. That was fun. Pi h over mw equals 1, which we can rearrange. A equals mw over pi h bar to the 1/4. I keep calling h bar h. Which means, I'm going to rewrite this, that our ground state wave function equals 1/4 This is our ground state wave function. I'm going to duplicate over here. I don't need that anymore either. Hey, this third board came in handy. Psi 0. But this means that we can now calculate, now that we know the ground state in the Schrodinger equation, we can plug that into the Schrodinger equation and solve for the ground state energy. So, E sub 0 times equals 1/2 mw squared x squared psi sub 0 h bar squared to m. Now I'm going to rename, because we're calculating second derivatives and they can get annoying, especially with this. We're going to say that for the time being that mw over 2h equals k. Psi sub 0 equals e. The constant factor that we just spent like 20 minutes calculating isn't really going to play into this because it'll just cancel out. So I'm not going to. We're going to say that first derivative of that equals negative 2kx e negative kx squared, and then chain rule, negative 2k e negative kx squared minus 2k x 4k squared x squared e negative kx squared equals 4k squared x squared minus 2k e negative kx squared, which is just psi sub 0 equals our second derivative. Now we're going to do 8 plus 1/2 w squared x squared. So k, as we defined it, ready to go, is mw, well 2k is going to be mw over h bar, and that's just m squared w squared over h bar squared, mw over h bar. That's going to cancel, plus h bar over 2 minus 1/2 mw squared x squared psi sub 0 plus basically the same thing, but that'll cancel out, equals e sub 0 psi sub 0. And that leaves us with E sub 0, the ground state energy, is h bar times w over 2, which I will rewrite. It's our ground state energy of this harmonic oscillator. So, but here's the thing. When we keep applying the raising operator, it'll take psi sub 0 to psi sub 1, the next state, with the next energy level, which has one factor of h bar added to it. Then the next state will have 2 h bar added to the E sub 0. It keeps adding on a number. Eventually our energy is just going to be h bar over 2 plus h bar times the which state you're in, which number state. And when n equals 0, it's just h bar over 2, and that's your ground state, and it just keeps adding as you go up and up and up. So that's the energy levels of our harmonic oscillator right there. And cut.